Hello everybody and welcome back to another visual pattern challenge. Here is our pattern today. We've got figure 1, figure 2, figure 3, and your challenge is to predict the number of triangles in figure 4. If you can do that, can you predict the number in figure 43? And could you write an equation that you could use to express the number of triangles in any figure at all? So that's the challenge. If you'd like to accept it, pause the video and work it out. Okay, so we've got kind of a strange looking one here. I think I'm going to begin by just noticing what's the same in each figure. And I've got a differing number of upward pointing triangles, but I've always got this one downward pointing triangle. So that stays the same. So in figure 4, I think there's going to be one downward pointing triangle here still, like in every other figure. Now let's look at what happens with the upward pointing triangles. So we have one, well, it looks like one row, then two rows, then three rows. So what I would expect there to be four rows in figure 4. And it looks like they get bigger as they go down here. So first there's a row of 1, then a row of 1 on top of a row of 3, and then 1, 3, 5. So continuing that pattern, I think I'd have 1, 3, 5, and the next row would be 7. And then we have this 1 underneath. So adding all that together, 7 and 3 is 10, plus 5 plus 1 is 16, 17 in figure 4. So that's my prediction for figure 4. But what kind of a pattern is this really? It looks like it's growing fairly fast, so I'm thinking maybe it's something other than linear. But let's go ahead and analyze the numbers. I'll put in the figure number here and the number of triangles here. And in figure 1, we've got 2. In figure 2, that's 5. In figure 3, that is 10. And in figure 4, we're saying 17. When we analyze the numbers like this, we take the difference between each step. 5 minus 2 is 3. 10 minus 5 is 5. 17 minus 10 is 7. And we're not getting a constant here. So the difference is changing from step to step. This means it's not a linear pattern. If this was all the same number, it'd be linear. When we find that they're different, we can try taking the difference of the differences. 5 minus 3 is 2. 7 minus 5 is 2. If that second order difference is the same, then you know it's a quadratic pattern, something with x squared in it. And it's a little hard to see the x squared in this pattern because of the way the shapes are arranged. But now that you know there's an x squared in here, you might see something in the numbers. This is kind of jumping out at me because these numbers are just one more than the perfect squares, right? If I were to make another chart here in figure 1, 2, 3, and 4, this is really 1 squared plus 1. This is 2 squared plus 1. See, that's 4 plus 1 is 5. This is 3 squared plus 1. 9 plus 1 is 10. And this is 4 squared plus 1. So that's one more than the squares of those steps. That insight is going to lead us to an equation. So I'm going to say the equation is the step number squared plus 1, just what I did down here in this second chart. So equation y equals x squared plus 1. We could test that with all those steps, but we kind of did that right here in this chart, so you can see how that all works out. And the only thing that remains is to calculate figure 43. So we'll put in 43 for x. So y equals 43 squared plus 1. And 43 squared is 1,849 plus 1 is 1,850 triangles in figure 43. Well, how did that work out for you? Did you predict 17 for figure 4? Did you see the perfect squares kind of hiding in the data here and come up with this equation that way? Or did you arrive at it some other way? Let me know. Thanks, everybody.